Hey everyone, and welcome. So, you're gearing up for an exam on transmission lines? Huh? Well, you are in exactly the right place. In the next few minutes, we're going to break down all the core principles you need to know so you can walk into that test feeling totally confident. All right, let's dive right in with the big picture. Before we get lost in the details, we got to answer the most basic question of all. What exactly is a transmission line? And, why do we even need one? The easiest way to think about it is like a special highway, but for high-frequency energy. Its whole job really is to get a signal from point A, the transmitter, to point B, the antenna, without losing a bunch of power along the way. And this is absolutely crucial when you've got some distance between them. Say the transmitter is inside and the antenna is way up on a tower. A regular old wire just wouldn't cut it. You lose way too much of the signal. Okay, so we know what they do. Now let's talk about what they look like. There are 5 main physical types that you're going to want to be able to recognize for your exam. Let's get into it. First up, we've got 2 of the most basic kinds. On the left is the 2-wire open line. It's super simple, but the downside is it kind of leaks energy and is really susceptible to outside noise. Then on the right, you've got the twisted pair. Now, that simple little twist, that's actually a pretty clever trick to help cancel out interference from, all the other electrical noise out in the world. Now, we're getting into some major upgrades. The shielded pair basically takes that twisted pair idea and wraps it in a braided copper shield. It's like putting armor on it to block out noise. And then there's the coaxial line. You've definitely seen this for your cable TV or internet. The genius here is its design, one conductor right inside the other. This structure is amazing because it traps all the electric and magnetic fields inside, which means you lose way less energy. And last but not least, we have the weird one of the family, the waveguide. So get this. Unlike everything else we've seen, this thing has no center wire at all. Yep, it's just a hollow metal tube. The high-frequency energy itself actually surfs down the inside of the pipe, bouncing off the walls. Pretty cool, right? So what's the big takeaway from all this? It's really simple. Form follows function. Every single one of these designs is a unique solution to a specific problem. It's always a trade-off between things like efficiency, how much it costs, and how well it blocks noise. This table right here is a perfect little cheat sheet for your notes, so maybe hit pause and let it sink in. Okay, so we've covered the physical stuff, what you can actually see and touch. But to really get how these things work, we have to go deeper into the invisible stuff, what I like to call their electrical DNA. This is what really controls how they behave. Okay, think about a normal circuit. You've got a resistor over here, a capacitor over there. We call those lumped components because they're in one spot. But a transmission line is totally different. Those same properties, resistance, inductance, capacitance, they exist everywhere, all along the entire length of the wire. They're distributed, and believe me, that changes everything. This diagram here is how engineers wrap their heads around this. The idea is to imagine the line as a crazy long chain of tiny, identical little sections. And each tiny little link in that chain has its own little bit of resistance, inductance, and capacitance. This model is absolutely the key to figuring out how a signal is going to act as it travels down the line. All right, so we've got the physical types and we've got their electrical DNA. And all of that builds up to this, the single most important concept in all of transmission line theory, characteristic impedance. Seriously, if you remember just one thing from this whole explainer, make it this. So, characteristic impedance, which we call Z0, is basically the natural resistance that a signal feels as it's traveling down the line. It's built right into the line's physical structure. It's all about that distributed L and C. And here's a huge point for your exam. It has absolutely nothing to do with how long the line is. It could be a mile long or an inch long. The Z0 is the same. And our whole goal is to make sure our antenna's impedance looks exactly like the line Z0. And here's the so what. Why do we care so much about this? It's because for maximum power transfer, you need what's called a perfect handoff. The impedance of the source, the transmission line, and the load must all be matched. When that happens, when your antenna's impedance is the same as the line Z0, boom, all the power gets delivered. It's perfect, no wasted energy. Okay, but what happens when that handoff isn't so perfect? What if those impedances don't match up? Well, that's when things get messy. That's when energy starts bouncing back where it came from. So anytime there's a mismatch in impedance right at the end of the line, some of that signal energy just can't get absorbed by the load. It's like it hits a wall, and a chunk of it reflects and starts traveling all the way back towards the transmitter. And that's just wasted power. So now you've got this chaotic situation with two waves on the same line. You've got the incident wave, that's the one going forward, and the reflected wave, the one that's bouncing back. And when these two waves crash into each other, they interfere and create this new wave, a resultant wave. We call this a standing wave because it looks like it's just sitting there, oscillating in place instead of moving. So for your exam, you see a standing wave, you should immediately think, impedance mismatch, wasted power. Whew. Okay, we have covered a ton of ground here, right? From the physical cables all the way to the physics of waves bouncing around. So to make sure all of this is locked in tight for your exam, let's do a quick rapid-fire review, and then I'll hit you with some practice questions. Okay, quick recap, let's go. The transmission line, that's our energy highway. Distributed constants, those are the electrical properties spread out all along that highway. Characteristic impedance, Z0, that's the highway's built-in speed limit. Impedance matching is making sure your car, the highway, and your destination all agree on that speed limit. A reflected wave is what you get when you hit a wall at the end of that highway. And the standing wave, that's the messy traffic jam that happens because of that reflection. You got these? You're golden. All right, question number 1. Can you list off those 5 basic types of transmission lines we talked about? Take a second. Okay, you should have two-wire open, twisted pair, shielded pair, coaxial line, and of course, the waveguide. Next up, what is the biggest advantage of a coaxial line? Think about that special construction. It's that concentric design, right? It contains the electric and magnetic fields, which really cuts down on radiation loss. Okay, here's a big one. What is characteristic impedance, or Z0? And what's our number one goal when we connect a load to it? Z0 is the line's natural, built-in impedance. And the goal is always to match the load's impedance to the line's impedance. Why? For maximum power transfer. All right, question 4. A standing wave is made up of 2 other waves. What are they? That would be the incident wave and the reflected wave. Okay, last question. Let's tie it all together. What happens to our energy transfer when a transmission line is terminated perfectly in its characteristic impedance? And why is that the ideal situation? The answer is, the load absorbs all the energy. There are no reflections, which means no standing waves, and you get a perfect 100% efficient transfer of power. That's the dream. If you nail those, you are in fantastic shape. If any were a bit fuzzy, just rewind and review that section. Thanks for joining me, and seriously, good luck on your exam.